Okay, so we're in a solver module now, solution module. The models, we specifically made a large first element height so that we could get fewer elements and go back to the k epsilon model, which is happy to have a big element. It's not for all problems, probably not for this problem, but I'm curious because I did a yplus around 1 mesh for the k omega model with SST. So we'll just see what this one gives us. And after that, we need a material is air by default. The boundary conditions inlet should already be pressure, and we just need to set an outlet pressure of negative 4,000 Pascal. So that's here, minus 4,000, and prevent reverse flow on that. And we'll prevent reverse flow on the inlets, though that shouldn't be a problem. But just for completeness, and we need some reports, so we will add a report on the mass flow rate, and we'll call that mass flow outlet, and choose the outlet surface. Say OK to that. And we're interested in a report on the average, the volume average for the velocity in the pod. And we'll report on that. And with that, we are good to initialize with hybrid and run some calculations, which will do 200 to start with and look at how it goes. So we will initialize and calculate. Okay, calculation complete for 200 iterations. Let's have a look at some convergence plots. And the mass flow rate is converging nicely around 0.0015. And I forgot to relabel this, but the velocity average is somewhat stable, near value of maybe 30. Could probably run some more simulations to evaluate that further. And let's make that plot that was shown at the beginning of the video, and that is a graphic. It's a path line. Path line is particle variables, and we could color it with particle ID or velocity, and put that emanating from these two inlets, and it's going to have, if you make a few more steps, then the path line at least gets out the outlet, most of them. So let's compute that and display it. Okay, that didn't take too long. And here's our path line solution, colored by velocity magnitude. If we want to fix up the color map a little, then we would just use general numbers and lengthen out the 0.8 on the length. 0.8. Here we go. Apply that. There we go. So there's our result, and we can see the highest velocities are in these in the grid area. And what I have is another simulation with a much finer mesh and a different turbulence model. Let's have a look at those quick. Well, I don't have the other model available right now, but another thing to plot is a contour of yplus, because I have had a target value in mind, and that is a quantity, I think, under turbulence. Yes, wall yplus. And I want to plot that on all the surfaces. So let's save and display that. And again, with the color map options, let's get rid of the exponential formatting and bump up the length a bit more. So we got a yplus around 19, wanting to get above 11 and potentially as high as 30. So it looks like I can increase the cell height of the first cell some more from the one we had. And the good news is with watertight meshing, I can just go back to the mesh, change one number, and let it recompute the mesh, and then hopefully this should just update and resolve to see if I have a better answer here. All right, so let's call that a success and see you in the next one. Thanks. Bye.